Okay, so let's say we have two boxes that are stacked as shown. The bottom box is pulled by a force F and slides across a frictionless surface, and the top block does not slide relative to the bottom block and goes along for a ride when the bottom block is pulled. So the first thing we need to do is draw a free body diagram for the top block by adding vectors that represent, and we should use on by notation. Okay, so we're going to have a block B, which is the top block. So this is B. This is A, which is the bottom block. Bottom block. All right, we're going to have an S, which is for the surface, and an E, which is for the earth. So by surface, I mean like this surface that A is on. So acting on block B, there's definitely a force of gravity on the block B by the earth, right? On by notation, on the earth by the block. We have a normal force, but it's not a normal force from the surface because B isn't on the surface. We have a normal force from block A. So we have a normal force on B by A. And then the tricky part is the direction of friction. So any type of friction that you want to figure out, you want to think about if this was a frictionless system, which block or how would the blocks slide? So if everything was frictionless, including this surface here between B and A would essentially get pulled out from under B. Okay? So at some instance, the edge of the block A might be here, and then at some later instance, the edge of the block A might be here, and so on and so forth. Okay? So because of that, because block A is essentially getting pulled out from under block B, block A would appear to slide leftward without friction. So friction's main job is to prevent that sliding. So in order to prevent that sliding, friction needs to act to the right because block B would slide to the left. Now this friction force, because A and B are at rest relative to each other, that friction force is going to be a static friction force on block B, and the surface creating that is by block A. Okay. So those are the three forces acting on block B. Now, a lot of people were confused about why this friction force needed to point in the direction of motion. Think about that forklift problem we did, right? The friction force is actually what's responsible for pulling block B along with block A, allowing those two to accelerate and move together. So the problem doesn't ask for it, but let's go ahead and draw a free body diagram for block A as well. Okay, so block A, of course, has our normal force of gravity on A by the earth, and then we have a normal force on A by the surface, and we have this applied force. Okay. Now we might think that those are the only forces, but remember there's these interactions between A and B. So any of our forces that are on B from A need to have a Newton's third law pair on A by B. So really, those two forces, the force of friction and the normal force, because they're due to the interaction between B and A, those are our third law pairs, and they need to have an equal vector but in the opposite direction. So let me make my dot a little bit bigger. So we're going to have a downward force, a downward normal force that really doesn't need to be bigger than the force of gravity on A. Let me make that a little bit smaller. When you're going to have a normal force on A from B, because B pushes down on block A, and then we're going to have a static friction force from A, or on A from B. Okay, so these two blue highlighted things are our Newton's third law pairs. And this is, of course, not to scale, meaning the size of my vectors doesn't matter and doesn't really represent anything. Okay, so these are third law pairs. So remember, anytime there's any interaction between two objects, if you can say that a force is acting on one object and is caused by the other, then if you're drawing a free body diagram for the second object, that force needs to have an equal force but opposite direction. Okay, and there's no kinetic force of friction on A because the coefficient of friction between A and the surface is 0 because it is a frictionless surface. Okay. And then we're asked to explain in words how we know the direction that friction acts. So like I said, friction acts opposite of the direction block would slide. This block would slide right without friction. So friction must oppose that. And act left. Okay. Now, where that can get a little bit tricky is, let's say that we have a block, okay, with another block on top of it. Let's say B, A, and let's say both blocks are moving together across the surface with a speed v, but these blocks are slowing down. So in our first example, we were accelerating our blocks from rest, but when we're slowing down, things become a little bit different. So the blocks have some velocity v, okay, and we are slowing down. The inertia of block B, okay, let's say that there's some force F slowing blocks A down. Okay. The inertia of box B wants the box B to keep moving in that forward direction. So without any sort of friction, box B would appear to slide forward. And you've experienced this in your car if you've ever had something in your like seat or on the seat next to you and you apply the brakes, that object appears to slide forward. So box B would slide forward without friction. Okay. But in this instance, there is friction, and box B and box A stay at rest relative to each other. So what that means is the friction force on box B must act in that leftward direction. Okay, and then we have a normal force from A on B, Earth on B, and this is A on B. Or if we're doing on by, I guess it should really be force of friction on B by A, normal force on B by A, force of gravity on B by the Earth. Okay. So again, we're thinking about if there was no friction, how would the box slide? And because this box A, the whole system is slowing down, if box B would appear to slide to the right. So to prevent that sliding, friction force needs to act to the left. So really, when the force of static friction causes the acceleration, and is the net force, which is the case with block B, but not with block A, because in block A we have the applied force that also acts as the net force. So when the force of friction causes the acceleration and is the net force, the force of friction is in the same direction as that acceleration and net force, because remember, acceleration and net force share direction. So the reason why that works is because if I'm moving to the right but slowing down, my acceleration and therefore my net force must be to the left. So the static force of friction on block B is what's causing this net force, so that static force of friction must act to the left. Whereas up here, right, this object was getting pulled to the left and this object was speeding up. So my acceleration was to the left and therefore my net force was to the left. So here, that's why static friction act to the left. Okay. Obviously, if our net force and our acceleration were to the right, then the static force of friction on block V would act to the right. Now, the reason, again, why it doesn't act to the right on block A is because, one, Newton's third law says equal in magnitude but opposite in direction, but also we have this applied force. Okay, so the static force of friction is not our net force. But really what we just need to pay attention to is the direction that the block would slide, and that would give us our direction of friction, because our direction of friction is opposite the direction that the block would slide. So hopefully that clears a few things up for you guys. Have a great day.